This lesson will be our last on Chapter 5, all falling into this overarching learning goal. Through inquiry and exploration, students will be able to understand that bonds hold elements together. We're specifically looking at ionic bonds in this chapter. The way in which those bonds are formed result in new compounds that can be represented by chemical formulas and nomenclature. And you've been assessed on writing chemical formulas and naming compounds as well as oxidation numbers. What we want to take a closer look at now are some properties of ionic compounds. So we know a bond is simply a force that holds ions or atoms together. And in the case of ionic compounds, you are holding ions together. When compounds are formed due to the transfer of one or more electrons, the compound is ionic. We know the metal loses electrons, the nonmetal gains electrons. For example, in the case of sodium chloride, a sodium atom loses one electron, forming a sodium ion. A chlorine atom gains one electron, forming a chloride ion. Electrons are transferred from sodium to chlorine, forming a sodium ion and a chloride ion. Ionic compounds are electrically neutral. The same number of plus and minus charge must exist in the compound. Ionic compound, sodium chloride. This is table salt. Similarly, aluminum ion, oxide ion, aluminum oxide, and again you'll have 2 aluminum ions, 3 oxide ions, 6 pluses, 6 minuses, electroneutrality that we talked about at the beginning of the chapter. So in an ionic compound, there is an electrostatic interaction between cation and anion. And again, the metal forms the cation when it loses one or more electrons. The nonmetal forms the anion when it gains one or more electrons. Now, when you consider ionic compounds, we have indicated already that the subscripts indicate the simplest whole number ratio of ions. It's not the true number that you actually have, and that's why when you write a chemical formula, after you swap and drop, you reduce if possible. For every 2 aluminum ions, there will be 3 oxide ions. So the subscripts are going to indicate the simplest whole number ratio of ions. Salts are ionic compounds. You'll see the ions are packed tightly together, resulting in a crystal arrangement. Some examples with the crystal lattice, the actual structure, are shown here. Sodium chloride, you don't just have one sodium ion to one chloride ion. You have a whole bunch, but however many sodium ions you have, you'll have an equal number of chloride ions. And you can see the structures shown here and here where you truly see that network that exists, similar to the jungle gym that I mentioned previously. Calcium fluoride also has a crystal lattice structure. Zinc sulfide, crystal lattice structure. That crystal lattice just shows the packing arrangement of the points or the ions. This is the structure that salts form. Typically, when you consider ionic compounds, you're looking at elements in groups 1 with 16 or 17, 2 with 16 or 17. But keep in mind, transition elements also can form ionic compounds, and they will form salts as well. For example, a group 1 with 16, sodium oxide, a group 1 with 17, lithium chloride, a group 2 with 16, magnesium sulfide, a group 2 with 17, calcium fluoride. But don't forget about your transition elements. A salt that we made earlier in the year included zinc chloride. All examples of salts. Salts are ionic compounds. Ionic compounds are formed through the transfer of one or more electrons from metallic cation to nonmetallic anion. One other distinction I'd like to make clear is when you have a polyatomic ion, in almost every case you will have an ionic compound. For example, sodium sulfate, ammonium chloride. The one that you need to be careful of is when you have a polyatomic ion that links with hydrogen. That will be covalent in nature. And I mention it here because in your project, this sometimes becomes a little bit cloudy. So for example, hydrogen sulfite, you don't have metallic cation here. It's named in an ionic format. You learned how to name that. But it is a covalent compound, and we'll come back to this in a little more detail when we talk about covalent compounds in the next chapter. Now, covalent compounds are formed through the sharing of one or more electrons. And what holds the atoms together is not an electrostatic interaction, but rather a covalent bond that can be single, double, or triple. And we'll explore that in the next chapter. One distinction you want to make clear at this point is if you have a covalent compound such as carbon dioxide, the subscripts now indicate the true number of atoms. You have one carbon for every 2 oxygen. It's not a simplest whole number ratio. Be careful, because dinitrogen tetroxide, and I'll teach you how to name these, you have 2 N's to 4 O's. And we're going to learn how to draw these compounds in the next chapter. Here's carbon dioxide, the gas you exhale. We're going to learn how to determine shape of molecules, polarity. You're going to see this has a linear shape or molecular geometry. You will learn that this is a nonpolar covalent molecule. These are all things we're going to explore. In the next chapter. For right now, what I want you to recognize, covalent compounds are formed through the sharing of electrons. The subscripts indicate the true number of atoms that you have in that compound. In addition, covalent compounds are comprised of 2 or more nonmetals that share electrons between them. Ionic compounds, you've got metallic cation, non-metallic anion. Covalent compounds, you will have two or more nonmetals that have combined chemically. There are many properties of ionic compounds, and we're going to take a look at some of them here. They are listed for you, but I feel this video truly illustrates properties of binary ionic compounds. Let's take a look at this video shown here.
Properties of ionic compounds. Ions are formed when metals lose electrons and non-metals gain electrons. Metals lose electrons because they only have one valence electrons, and non-metals gain electrons to get a full outer shell here. So what happens is sodium can give its electron to chlorine to become sodium 1 plus ion and the chloride negative ion. If you don't understand this, please have a look at my preceding video on ionic formation. Okay, so it's this electrostatic attraction between the anion and the cation which will form a very strong bond. And it makes this regular lattice shaped structure which has got alternating cations, which are the positively charged ions, and anions, which are the negatively charged ion.
And a really good question to consider is why the sodium ion has a smaller radius than the chloride ion. This is something we covered back in chapter 4, and you really want to make sure that the concepts we have addressed previously you have mastered. But you can see here this crystal lattice structure.
In the solid state, these ions are in a fixed position. So let's look at how this gives ionic compounds its properties. Ionic compounds are hard, they're solid, and they've got high melting points. The reason for these properties is the strong electrostatic attraction between the cations and the anions. If we look at the cation and anion here, they are attracted to one another. So what happens is they're attracted to one another and they form that close bond. This gives it this three-dimensional, strongly packed lattice structure, and that makes it a very strong structure, also a very hard structure with a high melting point. This structure is also responsible for making it brittle, and I put a picture here of peanut brittle because brittleness is about it being hard but being easy to break. Okay, so like peanut brittle will snap, salt crystals can break very easily. It means they're brittle, they can still be, or they still are classed as being hard. So here we have our alternating lattice structure. We have our anions and our cations alternating to form this regular lattice structure. Remember, the lattice structure is normally three-dimensional. Well, it is three-dimensional, but I've just represented it here two-dimensionally to explain what happens when a force is applied. So here's my force, and it pushes. And what happens here is that the like charges align to one another, and that causes those like charges to repel one another. And this repulsion causes the crystal to shatter, and that's what causes the brittleness. So if we have a look at an ionic crystal structure with a force applied, once that force is applied, those like charges align and it causes repulsion. The crystal lattice then shatters. Compare that though to a metal structure. When we push on a metal, the cations will move along, but those sea of delocalized electrons will just move around. And this is what makes metal hard but ductile and malleable, whereas an ionic crystal is hard but it is brittle. It breaks easily. And here's just another representation. So when a force is applied, the like charges line up with each other. You can see here, and they repel each other. The third and last property I want to have a look at is electrical conductivity in ionic compounds. For something to be able to conduct electricity, you need to have free moving charged particles. So some charged particle, whether it's an ion, an anion or a cation, or an electron that is able to move around the circuit. So with solids, we have this shape of a lattice here. They're held in fixed position of the ions. This means that there is no free moving charged particles, and thus solids are unable to conduct electricity. There is no free moving charge, so they cannot conduct electricity. On the other hand, when we look at an aqueous or a liquid solution of an ionic compound, you'll see here the lattice is a solid structure of salt. When that's put into water, that will break apart, and we now have cations and anions that are able to freely move around. So they're free to move, and they look something like this. And this means that they can conduct electricity. So here we've got free moving ions, and you can see when an electric current is applied, we have the cathode here, which has a negative charge, and it attracts the positive sodium ions, and on this side we have a positive charged anode, and that attracts the negatively charged chlorides. So if we have a look at this diagram here, distilled water does not conduct a current, and that's because water, pure water, is a covalent molecule, and we'll discuss why covalent molecules don't conduct electricity later down the track. But you can already tell from this that there can't be any free moving charge because you have to have free moving charge to conduct electricity. Here we have some salt, or a solid version of an ionic compound, and you can see here the positive and negative ions are in a fixed lattice position. So there's no free moving charge, so it doesn't conduct electricity. On the other hand, when this salt is dissolved in the water, you now have free moving anions and cations, and these are able to conduct electricity.
As shown in the video, you could see clearly that ionic compounds are hard and brittle, and they showed you that fracturing that occurs when a hard force is applied to the crystal. You saw the arrangement of the crystal lattice, as well as why salts melt and boil at high temperatures. Ionic compounds will have higher boiling and melting points than covalent ones. They also got into conductivity. In order for a substance to conduct electricity, it must contain ions, and the ions must be able to move freely. And while in a solid you do have ions, the ions are unable to move freely unless the solid is dissolved in water to generate an aqueous substance. This concludes our lessons on ionic compounds. At this point, you want a feel for some basic properties. You do want to understand that in a covalent compound, the subscript indicates the true number of each element in a compound, whereas in an ionic compound, it indicates the simplest whole number ratio. and the crystal lattice structure that exists for ionic compounds. You also want to have mastery of writing chemical formulas and naming ionic compounds. This is a critically important skill, one that will come back to haunt you if you don't master it at this time. So if you don't feel you do have a firm grasp on naming compounds and writing chemical formulas, you really do need to spend a little more time on classwork 2.1 and 2.2. We will continue with this learning goal in the next chapter as we explore covalent compounds. What you will need to do now is the mini assessment in your Google Classroom that will clearly show that you have watched the video and understand basic properties of ionic compounds, and you will also have a few questions on naming and formula writing to be sure that you understand how to do this critically important skill.